Hi, I'm going to talk about speed versus velocity. Now, speed is a scalar, velocity is a vector. This is going to seem at first a lot like the last video I did, but there's some really important differences between the two. So I want you to really pay attention and maybe even go back and rewatch the last video to see if it might help you understand some of the differences. Now, if you're ever confused about what's a scalar and which is a vector, like which has a direction with it, just remember speed, scalar, they both have s, velocity, vector, they both have v. So velocity has a direction because it's a vector, that's all those lines are drawing. Speed is a scalar, it does not have a direction associated with it. So let's start just like the last video. You go 3 meters per second to the east, you go 4 meters per second to the north. So this would be like, let's say you are going a canoe, right, to the east, and your speed is 3 meters a second, but there's a current that's carrying you to the north, so velocity northward would be 4 meters a second. These could be vector components of your resultant. So your resultant velocity, r, same 3, 4, 5 triangle, r is 5 meters per second at an angle of 53 degrees north of east. I'm going to write north so we don't think that's newtons. So this is your resultant velocity. And I'm going to demonstrate here one of the reasons why we break this into components. So sometimes you'll see problems where you only need to use one component of a particular problem. So maybe you know that the resultant velocity is 5 meters a second at 53 degrees north of east, but you want to find out, for example, how long it takes to cross the river. So let's say this is your river, and you know that your river is, for example, 16 meters across. But the river's distance is only going in that north-south direction, so that 3 meters a second component doesn't have anything to do with it. Like crossing the river, for example, doesn't have anything to do with how fast you're going east or west. It only has to do with how fast you're going north to south. So you could do a simple distance is velocity times time type of thing. Your total distance is going to be 16 meters because that's how far you're traveling north to south. Your velocity is 4 meters a second because that's your north-south velocity times time. So time ends up being 16 divided by 4, or 4 seconds. I'll put meters and meters per second in there. So sometimes you just need to figure out what component you're working with. You don't necessarily need to use all the components. Imagine this though, you want to know how far the boat goes east-west by the time you've crossed the river. So after 4 seconds, it's traveled, in addition to crossing the river, it's traveled, let's see, 3 meters a second times 4 seconds, 12 meters east. I'm going to step out for a second. So it's also traveled 12 meters east. You'll get more practice with problems like this as we go on. I want to start next, though, by showing you the same kind of graph that I showed you last time, but I'm going to make a couple of important changes. So I'm going to put this up here, and I'm going to erase the things that I had up before. And take a look at this graph, and just watch what happens as I change this graph from a displacement versus time to a velocity versus time. So now v is in meters per second. Time is still in seconds. And the graph looks exactly the same. And you might think it's the same kind of motion, but in fact it's not even remotely. Just changing the axes has made a very important, profound change in what this graph demonstrates. So think about it this way. This is now telling you velocity. So at time equals 0, its velocity is 0 meters a second. So it's basically at rest. It's staying still. But it doesn't stay there for very long because then velocity increases. then it speeds up. And then for another 3 seconds, it stays at a speed of 5 meters a second. So it maintains a constant speed. That constant speed would be 5 meters a second. Eventually, though, it slows down. And as it slows down, it will suddenly come to a stop at time equals 6. So it has stopped at time equals 6. And then it reverses directions. So remember, velocity is telling you the direction an object is moving in. So if the velocity is positive, this whole time it's moving forwards. Right here, it suddenly starts moving backwards. It's speeding up from time equals 6 to time equals 7, and then it's slowing down from time equals 7 to time equals 9. So it speeds up for a second from 6 to 7 seconds, and it slows down from 7 to 9 seconds. Totally different graph. So keeping in mind that right is positive, I'm going to walk this out a little bit. I am here, and at first I'm at rest, and then I speed up, constant speed, slow down, reverse directions, speeding up, reverse directions, slowing down. So it'll be like this. I'm going slowly, I'm going faster, I'm moving at a constant speed, I'm slowing down, I come to a stop, then I reverse directions, going fast, and then going slow. It's a little harder to walk this out. Apologies for the announcements. It's a little bit harder to walk this out. It's a totally different graph, though, and it means totally different things. You get more practice on this in class, but a couple of important things to note is that in the last graph we talked about the slope, right? The slopes of the lines haven't changed, the units have and the meanings have. So now the slope is equal to your acceleration. So from time equals 0 to time equals 2, your acceleration is now 2.5 meters per second squared. That's the slope. From time equals 2 to 5 seconds, your acceleration is now 0 meters per second squared. So you're not changing speed, you're moving at a constant speed. In the distance versus time graph, this plateau meant you weren't moving, now we are moving. 5 to 7 seconds, your acceleration is -4 meters per second squared. You'll notice the units of the slope are different this time too. So that means that every second you're going 4 meters a second slower. So if you start out at 5 meters a second, after 1 second you're going 1, and then after another second you're going at -3. So your speed is changing consistently at this rate. I hope this helps answer some of your questions regarding velocity time graphs. As I said, we're going to get more practice on this. One other thing that we will do in class, I'm going to mention briefly but not go over, is if you want to find distance with this graph, you can do so. And doing so involves basically creating looking for the area under the curve. So imagine, if you will, I want to figure out how much distance is traveled for those first 2 seconds. I can create a triangle there and say, hey, I know the area of a triangle is 1/2 times base times height. For a triangle, in this case, the base would be 2 seconds. The height would be 5 meters per second. So the distance it traveled during those first 2 seconds is 1/2 times 2 times 5. The seconds cancel out, you get meters, so you end up getting 5 meters. So it's traveled 5 meters in the first 2 seconds. If you want to figure out how far it's traveled from seconds 2 equals 2 to 5, that now is a big rectangle. So for a rectangle, the area is just base times height. So from t equals 2 to 5 seconds, the base would be from 2 to 3, or 2 to 5. 1, 2, 3. So 3 seconds is the base of that. The height of it is 5 meters per second. So it goes from 3 times 5, 15 meters in those 2 seconds. Much bigger number, and that makes sense that it should be because it's going much faster. If you want to find the total distance, it's traveled from time equals 0 to time equals 5 seconds. We can just add up our two results. We go 5 meters for the first 2 seconds, 15 meters for the next 3 seconds. That gives you a distance of 20 meters. So this object has traveled a distance of 20 meters in those first few seconds. A displacement of 20 meters also. The only time you're going to get negative displacement is if you have lines underneath the curve. Because again, it's always going in the same forward direction. Its velocity is changing, but it's always going forward for those first 6 seconds. Thank you very much.